Welcome Queen's students of Chemistry 112 to this week's tutorial. Today we're going to be reviewing nomenclature, and we're going to practice naming organic compounds with multiple functional groups. We'll start by briefly recalling what we've already learned about how to name compounds which have more than one functional group, and then we'll move on to some more complicated real-life examples. We'll practice naming some biological macromolecules like the basic monosaccharides, and we'll take a look at some more complex compounds, namely pharmaceutical drugs, which will have some more new and difficult functional groups that we haven't seen yet. First, let's recall why nomenclature is so important. From a fundamental standpoint, nomenclature is essential to understand because it is the language of chemistry. Just like English, which has words and specific rules, chemical nomenclature does too. These rules are governed and constantly updated by a body called IUPAC, which stands for the International Union of Pure and Applied Chemistry. The primary function of IUPAC and all of chemical nomenclature is to ensure that a spoken or written chemical name leaves no ambiguity concerning what chemical compound the name refers to. Every single chemical name should refer to one substance. To a lesser degree, IUPAC makes sure that every chemical substance has a single, standardized name. Looking back at the common prefixes, we've already learned that each number referred to in chemical nomenclature is associated with a Greek prefix. For example, a simple hydrocarbon alkane with 6 carbons in a linear chain would be referred to as hexane, hex being the prefix that is associated with the number 6 for 6 carbons, and the suffix ane representing the fact that this substance is an alkane, a hydrocarbon that only has single bonds. Another example is 2,3-dimethylpentane. Here the longest carbon chain, or the parent chain, is 5 carbons, so we label the alkane with the prefix pent and the suffix ane. Because this substance has substituents which branch off of the parent chain, and each has 1 carbon, we label the branches with the prefix meth for 1, and the suffix -ol to represent that they are branches. We also have to name which carbons these branches are on. Here it's 2 and 3, and because there are 2 methyl branches, we label them as dimethyl. When naming compounds with functional groups, we first have to identify the parent chain. Here there are 2 carbons, so the longest chain is ethane. Next we identify the highest precedence functional group. Here there's only 1, an alcohol group. The highest priority functional group gives its specific suffix to the chemical's name. So with alcohols being ol, the substance is named ethanol. When naming a molecule, the functional group with the highest priority will be the one which gives its suffix. Though it seems somewhat arbitrary which functional group gets priority, there is some correlation between the oxidization state of the central carbon and the priority of the functional group. Once you have identified the functional group with the highest priority, all other groups in a substance can be treated as substituents. So let's practice naming a compound that has multiple functional groups. Right off the bat, we see a hydroxyl functional group and a carboxyl group. According to the list, the carboxylic acid functional group, which contains this group of carboxyl, has the highest priority, so we can label this carbon as 1 and determine that the suffix for the substance will be oic acid. We can then count 4 carbons as the parent chain, and notice that the hydroxyl branch is stemming off of carbon 3. Putting all this together, we can determine that this substance's name is 3-hydroxybutanoic acid. The next molecule has another carboxyl group, which will once again become the priority functional group and give this compound the suffix oic acid. We next can see that there is an amine functional group, which we can see comes off of carbon 2 on the 3-carbon chain, and will be referred to with the prefix amino because we are treating it as a branch. Therefore, this compound will be known as 2-aminopropanoic acid. Okay, now we're going to look at some new functional groups, which have not necessarily been touched upon in class. First, here is a list of functional groups that are always written as prefixes and will never give a suffix, even if the substance they are attached to is just an alkane. These include halogens like bromine, chlorine, fluorine, and iodine, alkoxy groups of ethers, which connect to sides of alkane groups using an oxygen atom, azeto groups, which is an N3 molecule, and nitro groups, which is an NO2 molecule. Looking at the example on the right, we identify that there are 7 carbons in the parent chain, so this is a heptane molecule, and then we list off all the functional groups with their appropriate prefixes in alphabetical order. This leaves us with the name 1-bromo, 4-chloro, 3-nitroheptane. Here we see more functional groups that we haven't studied at Queen's in Chem 112 so far. And unlike the last that we just looked at, these groups will give their suffixes if they are of the highest priority. And generally they do follow the same priority rules regarding oxidization of the central carbon. These functional groups are nitriles, epoxides, disulfides, imines, acid chlorides, sulfides or thioethers, and anhydrides. While they are much less commonly observed than the main functional groups we've already learned about, they do come up from time to time, so it is important to be able to recognize and to name them. Now that we've had a full review on how to name organic compounds with functional groups, and we've also done some sample problems and learned about a handful of new functional groups, we're going to move on to some real-world applications of chemical nomenclature. Arguably the most important area of chemical nomenclature is biochemistry. Nearly all biological compounds have at least one or more functional groups because those are areas of the compound which let them undergo chemical reactions, and chemical reactions are what help the organism perform its everyday functions necessary to live. Glucose and fructose, two monosaccharides, can undergo a series of chemical reactions to store and produce energy in the form of ATP. Both glucose and fructose are polyols, and they have aldehyde and ketone groups, respectively, and when naming them, it is important to remember the rules of priority of functional groups. So what would the IUPAC names of glucose and fructose be? Glucose is an aldehyde because its carbonyl group is at the end of its 6-carbon parent chain. So by naming the carbonyl carbon as 1, we can locate the substituent hydroxyl groups of lesser priority on carbons number 2, 3, 4, 5, and 6. Therefore, the IUPAC name for glucose would be 2, 3, 4, 5, 6 pentahydroxyhexanol. Fructose's carbonyl group, conversely, is in the middle of the 6-carbon parent chain on carbon 2. So it is a ketone group and it will give fructose the suffix -one. Once again, we identify which carbons each hydroxyl substituent is on and come up with the IUPAC name of 1,3,4,5,6 pentahydroxy-2-hexanone. Now that we've looked at a biological macromolecule, we can move on to more complex practical applications of chemical nomenclature. Pharmaceutical drugs. A common analgesic drug is aspirin, or acetylsalicylic acid, which is used as an over-the-counter drug for pain relief. Aspirin is a good example of how some IUPAC names still use pre-IUPAC naming conventions over the current systematic rules because the names either sound simpler, are more concise, or because they are traditionally used and therefore not wanting to be changed. Some examples of pre-IUPAC names you might have heard that are still using current IUPAC naming, even though they don't follow the regulations, are formaldehyde and acetic acid. Now, often IUPAC will prefer to use acetyl instead of ethyl when describing a 2-carbon chain. To this day, IUPAC will still prefer using acetate instead of ethanoate when describing that 2-carbon ester. Part of aspirin's structure includes a variation of the acetate group, where an oxygen connects the acetate to another alkyl group. You might remember from the slide regarding functional groups that only give prefixes that this is called an alkoxy group. Knowing this, what would the name of aspirin be? Looking at the complete structure, we see that the alkoxy group, known as acetoxy, has replaced the second hydrogen on a benzoic acid structure. So we can determine that the official IUPAC name for aspirin is 2-acetoxy-benzoic acid. We've looked at glucose and fructose, but another essential chemical for us to be able to live is pyruvate. Pyruvate is one of the most fundamental chemicals in biochemistry because it is an intermediate in cellular respiration, a set of metabolic reactions that take place in an organism's cells to convert energy from oxygen molecules or nutrients, like glucose, into usable ATP. Pyruvate is the product of glycolysis, the first stage of cellular respiration, and it provides the necessary energy for the next step, the citric acid cycle, to proceed. Like aspirin, pyruvate has multiple functional groups, so we must first designate priority and then name them accordingly. The first thing to note is that there is a carboxylic acid functional group in pyruvate, which we know automatically becomes the priority, and this structure will have the suffix oic acid. Next, we identify that the other functional group is on the second carbon and that it is a ketone group. When a ketone is a substituent, it is given the name oxo. Putting together this information and realizing that the parent carbon chain is 3 carbons long, we derive the IUPAC name for pyruvic acid, which is 2-oxopropanoic acid. The last and most difficult chemical which we're going to look at today is another very common painkiller drug, which is used widely for fever and pain relief. The easiest way to go about naming a complex structure with multiple functional groups like Tylenol is to break the naming process into parts, and then put all the information together to come up with the correct name. So, first we circle the 3 functional groups of Tylenol to separate them. The group circled in green is a 2-carbon ethane amide, which would be normally referred to as ethanamide, but as we've already covered, IUPAC prefers to use acetyl over ethyl, so instead we're going to name it acetamide. The next functional group we notice is the blue-circled 6-carbon benzene structure, which will be called a phenyl group because it has a lower priority than the acetamide group. The last group we see is circled in pink and is an alcohol group. Because the benzene is treated as a branch, the alcohol group doesn't stem directly off of the parent chain connected to the acetamide, so we name it using a new, interesting technique where we're going to group the OH with the phenyl branch in brackets and treat it as one singular branch off of the acetamide parent chain. So, by grouping the OH and benzene into one molecule, which would be named 4-hydroxyphenyl, and we treat that as a branch off of the nitrogen atom in acetamide, we can determine that Tylenol's IUPAC name is N-4-hydroxyphenyl acetamide. Thank you all for watching this tutorial and have a great rest of your day.